Hello all, in this lesson we're going to be studying the acidity and alkalinity of solutions, and we'll introduce for the first time the pH scale, which is a scale we use to represent how acidic or alkaline a solution is. And we'll talk about the concentration of hydronium ions versus hydroxide ions before using Table M. The homework associated with this lesson is here. Please copy it down and make sure that you are ready to answer these questions in class tomorrow. And under that, copy down our aim today, which is, what is pH? Lastly, make sure you have these do now questions ready, just don't answer them yet. Okay, acidity and alkalinity of solutions. The type of bonding that exists in a molecule like water is called covalent, which means that since they're sharing a valence shell, their ability to dissociate is going to be relatively low. And therefore, you really wouldn't have much of either of those two ions, the hydrogen and hydroxide ions. So I'm not sure if it slipped past you just now, but this was water, the HOH. It's an unconventional way of writing it, but this is water, which we know is neutral, but it also does have the ability, although small, to make acid ions as well as base ions. This property is called amphoterism, or the substance itself could be referred to as amphoteric, which means that it can be an acid or a base. However, because water's dissociative properties are so low, it would be a weak acid or a weak base, if at all. So we can follow that idea a little bit further when I ask you the question, describe the acidity or alkalinity of a solution that has a concentration of hydrogen that is barely greater than the concentration of hydroxide. So, at least in this scenario with water, the number of hydrogen and hydroxide ions would have to be equal, meaning each water molecule as it dissociates would produce one H and one OH. But there are solutions that have more H than OH. And in the case where you have just barely more H than you have OH, you would be considered a weak acid. On the other hand, if we had a concentration of hydroxide, which was very much larger than the concentration of hydrogen, we would call that a strong base. So the pH range of an acid and the pH range of a base are things you may remember from middle school. For an acid, the pH range is from 0 to 7, and for a base, it's from 7 to 14. But actually, in both cases, the number 7 is not included because the number 7 is reserved for the neutral pH. So I suppose we could say 0 up to 7 for acids, 14 down to 7 for bases, but for the neutral pH, like water, it would be exactly 7. So pH is this sliding scale, or it's a spectrum, I suppose, that represents the concentration of hydrogen ions versus the concentration of hydroxide ions. For instance, down here where you have the most alkaline solutions, you would have much more hydroxide than you have hydrogen. Up here where you have the most acidic solutions, you would have much more hydrogen than you have hydroxide. So that's why we would find strong acids on this end of the pH scale, with the very low numbers, let's say 0, 1, 2. But there are weak acids and strong acids. For instance, battery acid is the strongest acid listed on this scale, and milk is the weakest acid listed on this scale at a pH just below 7. So in terms of dissociation of ions, battery acid is different than milk because battery acid has more dissociation and therefore produces a larger concentration of hydrogen ions. We can also find strong bases on this scale down close to the 14 side. Lye, which is one of the main ingredients used to make soap, is the strongest base on this scale. And in terms of dissociation, you would make sure that lye is different than baking soda because lye would have more dissociation and therefore would have a larger concentration of hydroxide ions. So let's talk more about the concentration of hydrogen versus the concentration of hydroxide, paying particularly close attention to mention the hydronium ion as an alternative to the hydrogen ion. So first of all, hydronium and where it comes from can be explained with this equation. We all know that hydrogen ions are characteristic of acids, but they're also going to be in the presence of water, so you'll have water mixed with acid at all times. When these two atoms and molecules collide, they can bond together in a temporary relationship that would be in equilibrium with the reactants themselves. And when they bond, they'll make a compound that has 3 atoms of hydrogen rather than 2 or 1 atom of oxygen, and it will have an overall positive charge as a result of being a neutral compound combining with a positive one. So this is the birth of the hydronium ion. And hydronium is really synonymous in every case with the hydrogen ion. You can use them interchangeably, and you shouldn't consider them as different. And the reason for that is that whenever you have hydrogen, you'll always have water as well, and you'll always have hydronium as well. Let's use hydronium to differentiate between acidic and alkaline solutions. So the acidic solutions would have much more hydronium than they would have hydroxide, and an alkaline solution would have much less hydronium than it has hydroxide. So let's get a little bit more practice with this concept. If you increase the pH from 7 to 14, you're going to be heading towards a more base or more alkaline solution. So you would notice that the concentration of hydroxide increases during that time. And if the concentration of hydroxide increases, you would notice a decrease in the concentration of either hydrogen or hydronium. Secondly, if you have a pH which decreases from 7 to 0, you're heading towards the acidic side of the scale. So you would notice an increase in the concentration of hydrogen and hydronium. And as those two ions increase, you would notice a decrease in the concentration of hydroxide that comes with it. I also have to point out some specialized vocabulary here. When we see the term an increasing pH, we often think that that means it's becoming more acidic. But increasing pH actually just means that you're going to a higher number on the scale, and higher numbers are actually bases. Conversely, if I reference a decreasing pH, oftentimes we would assume it's becoming less acidic. But in fact, a decreasing pH means that you're headed towards a pH of 0, which is the acidic side of the scale. I think the misconception that most people have is that they confuse or conflate the term pH with the term acidity. And pH actually covers acidity and basicity. So just make sure that when you see increasing pH, you know that we're headed towards 14, the bases, and decreasing pH means that we're headed towards 0, or acids. Okay, now this is where it's going to get a little bit weird, because we're going to acknowledge that the pH scale is actually a logarithmic scale, meaning that it's a tenfold scale. So if you increase the concentration of hydrogen by tenfold, you'll actually only notice a 1 unit change on the pH scale. So that's here. Conversely, the concentration of hydroxide is inversely dependent on hydrogen. So whatever you notice is happening to the hydrogen, it's the reciprocal is happening to hydroxide. So we'll do some examples together now. As compared to a solution with a pH of 7, how many times greater is the concentration of hydrogen in a solution with a pH of 6? So let's look at the 7 and the 6, and you can use the advice from up here. The concentration of hydrogen changes tenfold with every whole number unit. So if we go from 7 to 6, that's a whole number unit, and we're going from 7 down to 6, which means that you're increasing the acidity. And since it was a 1 unit change, then that means you have 10 times more acidity. In terms of concentration of hydrogen, that would mean 10 times more hydrogen. If you were going from 7 to 5, that's 2 whole number units on the pH scale. So you would get a times 10 effect, or times 100. And if you were going from 7 to 4, that's 3 units on the pH scale, so you would get times 10 times 10 times 10, or times 1,000. In this next example, we're going to examine how concentration of hydroxide changes, and I do advise you to remember that whatever happens to hydrogen, you're going to get the inverse with hydroxide. So sort of the same question. It's going to be 7 to 6 to 5 to 4. But instead of phrasing it as how many times greater is the hydrogen, I am phrasing it as how many times less is the hydroxide. You'll find that our answers are the same, but here's I'll go through them one by one. So if you go from 7 down to 6, you are becoming more acidic or less basic. So from 7 to 6, that would be 10 times more acidic, but it's also going to be 10 times less basic. So in terms of phrasing, it's a different answer, but I'm actually writing the same thing. If you go from 7 to 5, you're going to be becoming 100 times more acidic or 100 times less basic. And if you go from 7 to 4, you're going to be 1,000 times more acidic or 1,000 times less basic. Now, Table M is a reference table that shows us how to use indicators and when to expect their colors to change. So, I will go over these questions in a minute, but for now, let me just give you a tutoring session on Table M. So, methyl orange is an indicator that is commonly used. Basically, from 0 all the way to 3.1, the color of a solution in methyl orange would be red. Additionally, as you go above 4.4 and go from 4.4 up to 14, the upper limit of the pH scale, you're going to see yellow as the color. So above 4.4, 4.4 up to 14, you'll see yellow. In between 3.1 and 4.4, however, is where it gets interesting, because between those two, it's neither red nor is it yellow. It's a mix of the two. So you'll see orange inside that range. So from 3.1 to 4.4, it would be orange. Let's do another example for bromothiamyl blue. So for bromothiamyl blue, it's going to be yellow from 6 down to 0. And it'll be blue from 7.6 up to 14. So what color do you think it would be in between 6 and 7.6? If you're thinking green, you're right. And that's how we use Table M. Below the lower range, it'll be the color on the left, and above the upper range, it'll be the color on the right. In between, use your knowledge of color theory to make that color a mix or a hybrid. So let's answer the questions here on this page. What does Table M tell us? It tells us the pH ranges at which our indicators will change colors and what colors they'll change. Let's answer these questions. What does Table M tell us? It tells us the pH ranges and color changes for various indicators. And if we have a solution whose pH is 2 and it's in a solution of methyl orange, then you would be below the 3.1 range, so that would be red. On the other hand, if you had a similar scenario, only it were at pH 6, then it would be above the color change range of 4.4, and so it would be yellow in that area. And lastly, if we had a similar scenario, but it were at pH 4, pH 4 is right here in between 3.1 and 4.4, so it would be in the orange range. This one's a little more outside the box. Let's provide a range of possible pH values for a solution that's yellow in the presence of brome cresol green. So here's brome cresol green. I'll just highlight it for reference. It changes from yellow to blue between the pHs of 3.8 and 5.4. So if we need this to be yellow, then we also need the pH range to be below 3.8, because it's only yellow from 3.8 down to 0. So you may or may not have gotten to our titration lab, but if you haven't, when you do, you'll know that we use phenolphthalein as our indicator to indicate neutrality, on which titration depends. But after we can use Table M, we can see that phenolphthalein doesn't actually change color until it gets to pH 8, which is a good ways away from neutral, which is 7. So phenolphthalein, although convenient and dramatic, is probably not the best indicator to use if you're trying to represent neutrality. All right, let's watch this video about indicators from the Fuse School.
While it is possible to quantitatively measure the pH of a solution using a device known as a pH meter, there are also ways to determine pH qualitatively. In this lesson, we will learn about indicators, which help us indicate the pH of a solution. An indicator changes color depending on the pH of the solution analyzed. Because of this, they are also known as pH indicators. Universal indicator is very versatile as it can measure pH across the entire scale from 0 to 14. It is not a single indicator, but rather a combination of various indicators. If you look at the color changes of universal indicator according to the pH of a solution, you will find that it resembles a rainbow. If universal indicator solution turns deep red in a solution, it means that the solution is strongly acidic, with a pH of 1 to 2. If the universal indicator solution turns green, it means that the solution is neutral, with a pH of 7. If the universal indicator solution turns dark blue or purple, it means that the solution is strongly alkaline. Universal indicator paper works in exactly the same manner. Litmus is another indicator commonly found absorbed onto paper as litmus paper. Blue litmus paper turns red under acidic conditions, pH less than 7. Red litmus paper turns blue under alkaline conditions, pH greater than 7. Phenolphthalein is an indicator commonly used to determine the endpoint of a strong acid, strong alkali, or weak acid, strong alkali titration. It goes from colorless to fuchsia pink at a pH of 8.2. Methyl orange is used to determine the endpoint of either a strong acid, strong alkali, or strong acid, weak alkali titration. It is red at a pH lower than 3.1 and yellow at a pH higher than 4.4. In conclusion, indicators are substances that change color at a certain pH. The point at which an indicator changes color is known as its endpoint, which can be at any pH. Very common indicators that you will encounter are universal indicator, litmus in the form of litmus paper, phenolphthalein, and methyl orange.
And with that, we have reached our pair up. So please copy down these questions, which we'll answer in class, and follow it with these summary questions, and do include a sketch of this pH scale in your notes for the summary questions. Thanks for watching.